All right, we're in AP Stat. I'm still in Unit 1. We're on Chapter 5. We just got done going over ideas with variation and standard deviation, and there's a whole bunch of other stuff that we're focusing in on in this unit, and some ideas of comparing different variations, different sets of data to one another with z-scores, percentiles, quartiles, measures of relative standing, as well as basically what we are hitting up on now. This was basically the coefficient variance is where we left off in the last one. So remember we said that you can't compare standard deviations between different data, especially with different units. So we were just saying, right? We went over something called the coefficient of variance. That's what we just did. And that helped us compare two different variances to see which one varies more. Basically is what we were doing. It basically isn't used for much other than changing your standard deviation into some type of a percent. Is basically all that it's really used for. It's not really used a ton in the first place. But if you remember the test example we did, I asked you to see what percent of my data fell between 10 pounds and 58 pounds when I gave you that one. And I gave you a mean of 34, right? This process that we were doing helps us find something very important, and it's basically going to be called the z-score, is what it is. A z-score helps compare two data sets to see which one has more variation than the other. All right, so we can compare two data sets to see which one has more variation. Throughout this entire section that we've been doing, all right, so far, our job was really to compare measures between data or within data sets. That's basically what we've been doing. The z-score should look very familiar because we already basically did the z-score. All right, we just didn't call it that. All right, that's all it was. We just didn't call it a z-score. The z-score basically finds out how many standard deviations you are away from the mean. All right? It helps you figure out how many standard deviations you are away from the mean. The z-score is the number of standard deviations from the mean. And again, if I'm moving too fast through all of this, again, pause these videos, write down the notes, and move forward. Z-score is the number of standard deviations a data point is away from the mean. I basically said it three different but similar ways on here to reiterate this same fact over and over again. It's the number of standard deviations away from the mean. The z-score can be calculated for both a sample and population, so it does not matter whether you are looking at an entire population or just a small sample. Here is the formula for z-score for a sample. It is the difference from the point you're looking for and the mean, all right, divided by the standard deviation, okay, and that's of a sample. And for a population, same deal. It's just whatever number you're looking at minus the mean of the population, the difference between them over the standard deviation. And this tells us how many standard deviations we are away from the mean. This formula is good to have memorized and not just in the calculator because they are oftentimes going to have you manipulate it. Your calculator can find z-score, but they're going to want you to manipulate this little formula in order to find out what was the original number, what was the mean. If we give you the z-score, they're going to want you to manipulate it down the line. And if you don't know it, it's going to be difficult to do. Yes, we can get decimals. All right, keep that in mind. And this is basically a more exact way of doing the coefficient variation that we were just talking about. The coefficient of variance that we were just doing, this is just much better than that, which is why the coefficient of variance isn't used a ton. The z-score allows for a comparison of variations in two different samples of populations. So take a look at an example. If we are going to compare Lyndon B. Johnson and Shaq, right? Obviously, everyone wants to compare those two, right? Lyndon B. Johnson and Shaq. And what we're looking at is Lyndon B. Johnson, all right, his height was about 76 inches tall. And the mean population for all presidential heights, is what that's supposed to be, heights, is 71.5 inches tall with a standard deviation of 2.1. All right, so every president that we've had, Lyndon B. Johnson, 76 inches tall, basically the mean, right, was 71, and the standard deviation was about 2. Okay, so he's above the average. Shaq's height was about 86 inches tall, and the mean heights for all the, and we'll go with Miami Heat players, using the data when he played for them, was 80 inches was the mean, with a standard deviation of 3.3. Okay? So the question is, who's relatively taller. Everyone looks at it and says, well, Shaq's taller. Shaq is taller, but to his pool of people who you are looking at, who is actually more tall is what we're looking at. So who's relatively taller? Everyone wants to say Shaq, and he is absolutely taller. We can all see that. He is taller than Lyndon B. Johnson, but is he relatively taller to his population? Most people who play basketball are naturally taller than everyone else. So let's use the z-scores to do this. And note, you can get negative z-scores. It's fine. It just means it's on the negative side of the mean, as in on the left side of the mean. So Lyndon B. Johnson used population, since it is every president up to that point. So when we do that, it is the 76 is his height minus the average divided by the standard deviation. We find out that he is 2.1429 standard deviations above the mean, is what we find out. All right, the z-score for Shaq. Use population since it's all Miami Heat players used. All right, so all the Miami Heat players that are ever there, that's their average height. That's his height. Divided by that, it's 1.8182 is the standard deviation. So Lyndon B. Johnson is 2.14 standard deviations away from the mean, while Shaq is 1.82 standard deviations away from the mean. So Lyndon B. Johnson is relatively taller, right? 2 standard deviations from the mean is considered usual, right? If you're within 2. Shaq is within 2 standard deviations of his population. So he isn't abnormally tall, but Lyndon B. Johnson is right outside of that mark, right, of being usual. Lyndon B. Johnson is not usual, since he is right outside of his 2 standard deviations. However, Shaq is considered usual, all right? Lyndon B. Johnson is relatively taller to his population. Both are taller than most, right? Both were taller than the mean, but Lyndon B. Johnson is taller to his population. All right, now, do you remember the empirical rule that we were talking about, right? 68, 95, 99.7, right? Remember that? 98% of the data is 1 standard deviation away from the mean. This means you get a z-score of 1 or negative 1 in between there, right? If it's 1, you are 1 standard deviation above the mean, right? If it's negative 1, you are 1 standard deviation below the mean. Anything in that range is usual, is what we're saying. 95% of the data is 2 standard deviations away from the mean. This means, right, that you get a z-score of 2 or negative 2. So if you get a 2, you are 2 standard deviations above the mean. And if you get a negative 2, you are 2 standard deviations below the mean. Anything in that range is still classified as being usual. 99.7% of the data is 3 standard deviations above the mean, right? And below the mean. So again, 3 above, 3 below is what that means. Anything in this range is unusual, as in above 2 standard deviations. So anything that is definitely above that is definitely rare, is what they're saying. Here is the graph, again, of the normal distribution with the z-scores. Become very familiar with this. These z-scores are very important to remember, because ultimately, once we get farther along in this course, our job is to try to connect the dots and make every data set fit this generic normal curve that also has the same z-scores and standard deviations, so we can compare all data sets to the same thing. That's the intent. Z-scores are mainly used to show how usual and unusual data is. That's the point. How usual and unusual it is, depending on where it falls. Z-scores are mainly used to show that for this purpose. Everything in here from 2 standard deviations, that is classified as being usual. So it usually happens. Eventually, when you guys start really diving into statistics and you're trying to find outliers, you're trying to find how usual something is to happen, it all falls within this range as being usual, plus or minus 2 standard deviations. Anything outside of that little range there, right? That's considered to be unusual. What if Lyndon B. Johnson played for the Miami Heat? If we put him in the data set, would that be usual or unusual? The point is, all right, where would he fall in that perspective? Side note, Lyndon B. Johnson being on the Heat would change the average height, okay? So this is fuzzy math that I'm showing you to get the point across, okay? It would change the standard deviation. Since I don't know the data set off the top of my head of every single Miami Heat player, I can't give you the most accurate answer possible. All right, keep that in mind. But the point is, if I just use the mean and standard deviation that we have with him, he's actually below the mean. And he probably would be below the mean. Now, where exactly, I don't know, depending on where he is. But he'd probably be more on the smaller side of people who play basketball, just naturally. Makes sense what I'm getting at here with this. Since it's between -2 and 2, he's still usual, but now he's technically below the average height of all players that were on average on the Heat. The larger the absolute value-wise, like the larger the z-score means the more rare it is from happening. The larger that z-score, absolute value-wise, all right, it means the more rare it is. So now let's talk about something called quartiles. A quartile is a way of breaking up your data into sections. Don't overthink this. You're breaking the graph into quartiles or quarters, right? So you're breaking it up into 4 sections. First quartile, all right, represents the first 25% of the data, all right, quarter, 25% of the data. The data must be sorted in order from low to high, right? The second quartile, which you know as the median, represents the first 50% because that's 2 quarters of the data, all right, in order. The data must, again, be sorted from low to high. The third quartile represents the first 75% of the data in order, 1, 2, 3, right, quarters. The data must be ordered from low to high. And there is no fourth quartile, all right? And the reason why is because it would be the very, very top, the 100%. And oftentimes in statistics, we're not going to have 100% of anything. We are separating our data into 4 sections. But again, when there are 4 sections, there's technically only 3 cuts that are being made to make the 4 sections. Okay. Remember, the calculator does show us Q1, Q3, and basically Q2 is the median. So you are getting those 3 when you plug stuff into your calculator to get that data set. The calculator will even put the data in order for you, so you do not have to waste your time doing that. So we're going to try an example, but I'm going to wait until we come back with the next video in order to try that example. Okay.